Yes, hello my dear students. Welcome back to the St. Joseph Composite PU College, Vijaypur. I am Rahul, chemistry faculty, and in this video I am going to discuss the one of the important concept known as colligative property. Before we go for the understanding the colligative property, let me take one simple example to understand that what is or what are the colligative properties. One thing that sweetness, let me write here sweetness is a colligative property if I considering it. Just assume it's not colligative property, just assume it is a colligative property. So how it is a colligative property? And to understand that, you have to take a glass. You have to take a glass, and in that you have to add 1 gram of sugar and water. You make sugar water solution and taste it, and that taste you refer it as X. You keep in the mind that whatever the tastiness is, strength of the tastiness is there, that should be X. Now in that you have to add 9 gram more, and that total becomes here 10 grams. Again you check the sweetness. The sweetness is increased by 10 times. Means the sweetness is the property which depends upon the number of sugar particles, right? The number of sugar particles. Like that way, here the colligative property are the properties which depends upon the number of solute particles. That depends on the number of solute particles. Let me write that. So these are the properties which depends on the number of solute particles, but not the nature of solute particles, and not on nature of solute particles. What is the meaning of nature? So whether it is a polar or non-polar, whether it's a liquid, gas, whatever, it is not dependent on that. It's not depends on nature of solute particles. Okay, hope you understood this, right? So what are those solute particles now? What are those colligative properties? We'll list all those colligative properties here. The first colligative property we can list here, that is the relative lowering of vapor pressure, that we discussed in the previous time, right? Relative lowering of vapor pressure. The second one is about the elevation of boiling point, students. Elevation of boiling point. That boiling point of the solution get increased as compared to the boiling point of the solvent individually. Now second one is, that is depression of freezing point, students. The freezing point of the solution get decreased. Like for example, water freezes at 0 degrees Celsius, it converts into ice. But when you add some non-volatile solute like salt into the water and make it freeze, and when at 0 degrees Celsius, you can say that the temperature of the ice is less than 0 degrees Celsius. The temperature or freezing point of the solution is decreased. Okay. Now the last one, and my favorite, that is osmosis or osmotic pressure. So these are the few, you can say that colligative properties are there for your syllabus. We'll discuss it detailed. Okay, now come to the first one, that is relative lowering of vapor pressure. The first one, relative lowering of vapor pressure. Very simple concept is there. It is already explained, but even though I will explain it once again, because the same explanation we have to extend to determine the molecular mass of the solute. Okay, so for that I need a container. Let me draw one container here. Okay, this is a container, and this is the level of the water or some kind of solvent, and in that, at the surface, you can see that there are solute particles, solvent particles are there. These are the solvent particles present at the surface. Even at the inside also they are present randomly. Now what I will do, that I will add some non-volatile solute. Before that, I want to know that one thing, that students, at the surface you can see that more number of solutes are there, right? More number of solvent molecules are there, and therefore what happens here, more vaporization will take place. But when you add the solute particles, non-volatile solute particles, they are occupied at the surface, and they are also present inside, no doubt in that. But here what happens, the vaporization decreases, and whatever the vaporization takes place, that is the vaporization of the solution. Because in that non-volatile solute is present now. Now the blue color particles are called here as A. This is A, and yellow color particles are called here as a B. They are B. Okay, what are A and B? Will write that. So A is what? It is a solvent. Particularly it is a volatile solvent. Volatile solvent. It's a volatile solvent. Okay, and what about the B? B is non-volatile solute. Non-volatile solute, students. It is a solute, not a solvent. Okay, it's a solute. It's a non-volatile. It's not easily get to evaporate at the room temperature. Now, whatever the pressure is created, this is the pressure of A itself. Therefore, I will write here P of A, the partial pressure of A. Let me write this one. This is a partial pressure, partial pressure of A component it is. Now, the total pressure, if I write here total pressure P is equal to P of A plus P of B. I going to write P of A plus P of B. That is a Dalton's law of partial pressure, where the total pressure of any mixture of components, if you have, then it is the sum of the partial pressure of individual gases, right? But the problem is the PB. The PB can be given as, from the Raoult's law, it is Raoult's law, it can be calculated as P naught B into mole fraction of B. But the problem is P naught B of non-volatile solute at given temperature is 0. That is P naught B equals to 0. Why it is 0? The 0 is because it's a non-volatile. So therefore what will do that P naught or PB is there, no? So that becomes 0. Therefore, whatever the total pressure is there, no? Total pressure that is contributed by only PA. Okay, therefore I will write here P is equal to P of A. That the total pressure is equal to partial pressure of A component, not a B component is included in that. According to Raoult's law, we will apply here according to Raoult's law. Okay, Raoult's law. We will apply the Raoult's law here, student, for the that solution. That is PA we can calculate. The calculation can done by the multiplying the partial pressure of A component at its purest state and multiplied by the mole fraction of A. Okay, now let me take this equation as 1 and this equation as 2. This is equation number 2 and equation number 1. We have to compare both equation 1 and 2. We'll get new equation, that is P is equal to the P naught A into mole fraction of A. Okay, this is the equation. We don't want here mole fraction of A. We need mole fraction of B. Why? Because we have to explain how much solute is dissolved and how much vapor pressure is decreased. That we have to calculate. And therefore what I'll do that, we know one equation, that is mole fraction of A plus mole fraction of B is there, no? That is exactly equals to 1. In that case, if I write here mole fraction of A equals to that, it becomes 1 minus mole fraction of B we get. Okay. Now this will be the equation number 3 and this will be the equation number 4. We'll combine the equation 1 and 3 and 4 will combine, and by that what you get 4 and 3 we have to combine, right? Okay. So P, that the total pressure P is equal to the P naught A, keep as it is. The mole fraction of xi A is there, that is A, that we can write here 1 minus mole fraction of B. Okay. So now we'll simplify this. We'll get here P equals to P naught A minus P naught A into mole fraction of B. Okay, we'll simplify one more step here. So what do you get there? That's a P minus P naught A is equals to minus P naught A into mole fraction of B. So for this equation we have to multiply with minus 1. Multiply by minus 1 on both sides. Okay, both sides we have to multiply this. And when you multiply this, we'll get here, that is a P naught A minus P. It gets interchanged. Okay. So now here we get P naught A into mole fraction of B we'll get. So again we can simplify here. We can do one thing, that is we'll take the P naught A on the other side. It becomes P naught A minus P, the whole divided by we'll write here P naught A. So that equals to xi B. In the previous class I was explained that the P naught A minus P is the quantity which shows that how much vapor pressure is decreased, and that decreased whatever the quantity is there, if you melt if you want to relate with the P naught A, then it is called as a relative lowering of vapor pressure. This term itself is called as a relative lowering of vapor pressure. This is explained in one of the previous video. Go and check that. And here mole fraction of B. And we can say that the relative lowering of vapor pressure is totally dependent upon the mole fraction of B. Okay. So using this, we're going to calculate the molecular mass or molar mass of the solute. So let me write the statement, or you can say first heading here, the determination of that is molar mass of solute in a solution. Okay. So whatever the above example is there, no, same example we have to take and explain this. And now we'll take the relative lowering of vapor pressure, that is P naught A minus P, the whole divided by, that is a P naught A, and that equals to we'll write here mole fraction of B, that is solute B. But we know that the mole fraction of B can be given as the number of moles of component B divided by number of moles of component A plus component B we have. We know this, right? This is equation, this is a generalized equation for the mole fraction. But what we know here, that if you compare Na, number of moles of solvent and number of moles of solute, the solvent molecules are very large in number. And because of that, NB is ignored or neglected. It is neglected. So only in the addition, in the denominator. And for that, what we'll get here, that is this term, that is a mole fraction of B is equal to NB divided by Na we get. We left out the NB only at the denominator, not at the numerator. If you do it at the numerator, it will be infinite. It have no meaning for that. Okay. So after that, so we'll combine these two equations, the first equation and the last equation, that is a relative lowering of vapor pressure, that's P naught A minus P, the whole divided by P naught A, that equals to NB divided by Na. So this is what we get now. But thing is that the number of moles of solute B can be given as given weight of solute B divided by molecular mass of the solute B, and that should be whole divided by the solvent moles can be calculated by the given weight of solvent A, then the molecular mass or molar mass of the solvent A. Now we'll simplify one more step here. What do you get here? That's a P naught A minus P whole divided by P naught A, and that equals to, students, this is, be careful, we have to simplify this term here, that is WB, so divided by MB, and that should be multiplied with MA divided by WA, student. This is what we get final equation. Now what I will do that, we want to calculate here the molecular mass of the solute. You can see that determination of molecular mass or molar mass of solute here. So that is MB we have to calculate. Let me write here MB we have to calculate. And for that, what I will do that, I will write here MB is equal to, so I will just interchange here. This becomes WB into, okay, I don't want to write here into dot MA, these two terms are multiplied here, and then this entire term relative lowering of vapor pressure, this should be written at denominator, that is a P naught A minus P whole divided by P naught A, and then it is multiplied with a WA. Okay, so this is what we have, the equation, and this equation we use to calculate the molecular mass of the solute if we know the relative lowering of vapor pressure, students. So this is all about the you can say relative lowering of vapor pressure. Hope you understood this. Thank you for watching this, students.